Yes, I think we're ready.
Yeah.
We're not seeing it go.
No, we're not. This is not the right one.
It should be.
Okay, thanks for waiting, everybody. We are just getting started on this topic.
I think give it a couple seconds, it'll probably appear.
That's pretty optimistic.
Something's happening. Yeah.
You are right, Marcus. You are right, Howard. Yeah, good.
Now he's got his microphone on. He should probably have it on.
It's muted here.
That doesn't matter. The speakers will. Yeah, if you go back to, I think put it on phone call.
Oh, cool. Okay, I think we're good. Yeah, you can minimize that.
Okay, so yeah, I'm just going to go through an update on what I've been looking at with the recurrent sparse memory, which was a model we went over several weeks ago. So just for a reminder on what that architecture looks like. So this is HTM-inspired recurrent neural network that's designed for sequence learning tasks. And so the way it works is we have n groups and n cells per group, just like HTM, and each column, they call these things groups, we'll call them columns. So each column of cells is going to be having shared weights from the proximal input. So this is showing like an MNIST digit coming in as input, and each cell has recurrent inputs from all the previous, the entire previous memory state. So the red connections there are from the previous memory state, and the blue connections are
So this is so far just the HTM sequence.
Yes, in sort of a deep learning framework, or in sort of a RNN. These are continuous weights, for example, not binary. And the constraints that the original authors held themselves to was this local credit assignment and no time traveling synapses. You can't have direct connections to previous time steps. You only get direct connections to the previous memory state. So all the hidden state of the network has to be encoded in the memory. There's a nonlinearity via k winners. So they take k columns and one cell per column to activate. They decode through a final layer, and they're producing image prediction of what the network expects the next image to look like in the sequence. And then they use MSE loss function to optimize. No. Okay, so how do I switched it to the next slide.
Oh, but you're not
You're actually sharing an application window.
Okay, that's sharing Firefox.
You can see what's going on by looking for some.
Yeah, you should just share my screen and your message.
Oh, you showed the screen. Okay, screen.
Yeah, that'll work.
Good, okay.
Checking this
Yeah.
part.
Okay, so yeah, so I'll just remind everyone what the RSM architecture looks like. The tasks that we're testing with, one of them is we're calling stochastic sequence MNIST, and so the way this works is we define a grammar of subsequences. So the benchmark grammar that we've been using, and the authors at AGI.io were using, as well as this grammar shown there. So each row is a subsequence, and the way this works is you move to the subsequences deterministically. For every label or digit there, we're going to choose randomly an MNIST digit from the MNIST data set, training data set. And as soon as we get to the end of any subsequence, we're going to randomly select another subsequence to start on. So the goal is a pixel level image prediction, but and the grammar is generated in this way. So the network is never seeing labels, they're just seeing pixel level images, and it has to both solve MNIST by classifying MNIST digits as well as predict the next item in the sequence, and so learn each of these subsequences. The second task that we looked at was this language modeling task with the Penn Tree Bank data set, which is 1 million words from the Wall Street Journal, reduced to a vocabulary of 10,000 words. And the goal is to predict the next word based on the entire sequence up to the current. And they're not using any embeddings because they're interested in seeing whether an RSM-like architecture can develop meaningful embeddings in and of itself. So this is an example of the output from one of these rollouts of predictions. You can see that it's doing an okay job. This is something that you might get out of like a 2-gram model as well. So it's able to, for example, predict that after New York Stock Exchange composite were the next words. But I'll show results a few slides later. So I started with this RSM model, just re-implementing, trying to replicate the results from AGI. I haven't perfectly replicated the RSM model yet, and I'm having a call today to try to look at for the details of what exactly the differences are. But I did start to see some results that were interesting enough to adjust the model a little bit and try a few tweaks. So the first thing that I was looking at was using 2 winner cells per column instead of 1, and using our k-winners and column boosting instead of the inhibition that the original RSM model uses. And one of the things that was interesting was that the column level representation, so the image predictions are decoding from a max pooled column level state. So we're taking the max of cells in each column, and that kind of column level representation is what actually produces the decoded next image prediction. So what I was hoping to see was differentiation between different representations of the same input. So what's showing on the right here, 0, 1, 0, 2. So this is like we've just seen a 0, and we're about to see a 1, or about to see a 2. We need these to be represented differentially. We need to be able to discriminate between these cases so we can make a correct prediction for the next time step. And what these blue boxes on the diagonal are showing is that there's no column level differentiation. So the column representation of each of these 0, 1, 0, 2, essentially the same label, different predictive state, is identical. And what that means is that we're going to get ambiguous
Isn't that
image
the whole
predictions.
point of having the columns in this individual cells? I mean.
Yeah, hypothetically, the cells are representing the predictive state, and the columns are representing the feed-forward input.
Yeah.
But the way that the RSM is constructed is we're actually decoding through the column, the kind of the max pools column level activation memory. And so the result is that you get these really ambiguous.
So it's not going to work. I mean, so it's not
it
surprising,
works.
right?
It works okay, but it doesn't work very well.
Well, you can't really differentiate between these, so that's sort of the key thing about sequences, right? Am I missing something?
There's some nuance, which is this: so even though we're producing predictions based on the column level activity, when we're assessing its ability to do predictions at the label level, we're actually decoding from the entire memory state. So the images that you're seeing down in the lower right are based on the column level activations, but the decoder is actually predicting from the entire memory state. But the loss function is optimizing against this. So
Well, okay, so that's kind of weird. It's sort of like saying, imagine we would say, oh, I have a union of predictions because there may be multiple things going on, and I'm going to make an image prediction based on that union. Well, it's going to be blurry.
Yeah.
But if I make my accuracy prediction, or I predict the next element, what it is, then I could use the individual cells and that'll work. But you would expect it to be blurry in this case, right? I mean, we're not surprised by that.
we're not surprised by that. And so the idea is that perhaps if this is the primary loss function we're optimizing against, then maybe it's producing some sort of floor, and yeah, because we're optimizing.
Yeah, that's impossible. So
It's impossible to
I'm
get very
surprised
good
it works at all then.
but it is able to develop representations that are able to learn simple subsequences. I think the authors report getting to maybe 83% of 86%.
Well, if there's a really, really common subsequence and that's unique, then it could work. But if there's a lot of ambiguity in the 0, 1, 0, 2, 0, 3, 0, 4.
Yeah, so by definition, we have a lot of ambiguity because we have all the different subsequences we might be part of.
Yeah.
And so we're at any given digit, we have to be predicting multiple nodes.
Yeah, and then.
I think we decided this was at most second order. It's not a real high order problem.
Exactly.
Yeah, okay.
Yeah, so
that
we can do
makes
it.
sense.
Yeah.
Take to separate somehow, you're predicting through the 4 different numbers, can you separate this representation somehow?
Yeah, so we want the representation to be maximally separated for sure.
Well, the way you separate them, at least the way we do it in the sequence memory, the HTM sequence memory, is that you have essentially the set of neurons are decoding simultaneously the union. So every you would predict multiple things based on multiple previous states. And you could just put a classifier of some sort that says a certain subset of cells always represents this, and another subset represents that.
Yeah, exactly.
It could be done.
So this was this was inspired by HTM. This is why they did it this way. Exactly why they're decoding through the max pooled versions, I still am not totally clear on. I think there was some argument for keeping the number of parameters low, but decoding from the full memory state, I think makes more sense. And when they're doing the predictions, they are using the full memory state. It's just for the image production, which is the primary loss metric, and they go down the column of activations. So it's true that one solution to this problem is we use HTM style, and we just decode through the full memory state. I speculate that there's some limitation to that structure, which is that we have to learn a predictive state for every single feed-forward input. So we have to learn a different subset for 0 to 1 as we do for 2 to 1, as we do for 5 to 1.
Yeah.
So every input representation has to learn all of its predictive dynamics. And there's something that feels a little bit inefficient about that. It seems like there could be some additional efficiencies from learning that certain cells are just representative of I'm predicting 2 right now. And that those same cells can be
If you think about like melodies, I mean, it has to do this, right? any particular node. You only have a few nodes in some sense, few intervals. And every melody is composed of some sequence of these few intervals. And therefore you have to have, you just have to be right with these unique representations for all these transitions. I think the trick is, you don't want to remember every subsequence for all time. It's like the things that repeat a lot, then those are the ones you sort of relearn, and the other ones, the things that don't happen often, you come to that. I understand what you're saying, I'm not sure, but there is a real advantage to doing it the way the HTM model does. It's and I don't think it's not going to be a capacity problem if you do the right one.
Yeah, I don't think I'm making a capacity argument. I think I'm making potentially a learning efficiency argument that it might be useful to have certain cells that share this predictive aspect. So if we know that the next node is going to be a C, could it be useful to represent the previous node with some cells that are shared between
Okay,
that are
I don't know why that would be more efficient, but it's not clear to me why that would be more efficient at all, but
I think there was there wasn't, another issue is to have representations here that would have some semantics to them, rather than completely orthogonal representations. And so if there was some information about the nature of the sequence, independent of the exact inputs that you're getting, then that might be helpful as well.
Yeah.
The semantics, for like one aspect of the semantics would be that this particular input is going to be followed by the same next input. And so you might want some sort of overlap between representations that are both directly prior to the name.
Yeah, I think the way the brain does it is much more complicated. And we didn't understand it actually when we did the sequence memory. We didn't have that semantic representation. We knew we didn't have it. And I think the solution to that is going to come about from the work on
The locations.
yeah, the whole location, where the displacement cells, thank you. The displacement cells, which sort of capture more semantic meaning, in sequences, the semantic meaning is a third, not a C to an E. Right, the specific thing is C to E, and the third is a more semantic representation. There's many things that represent a third, but individual things would. So you have to have both in some sense, and that was captured. We haven't worked it out, but that would be captured in the displacement stuff. Yeah. So doing it this way is okay. Maybe it'll work. It's a little funky. I don't know what happened. You're going to tell us.
Yeah. So I mean. Right. So the RSM style is through these kind of max pool versions. So I was interested in trying to encourage representations that were more differentiated differentiated by the predictive state, by which next input they're predicting. So I was looking at a flattened version as well. And so the flattened version of this is a cell-only architecture. So there's no weight sharing. Every cell takes it's a unique weight matrix from input, and a unique weight matrix from the previous recurrent state.
So you're no longer activating mini column, is what you're saying?
There isn't really a notion of mini columns anymore.
Okay.
So we have all cells are the same, and they're all taking input from P4 state, and they're all taking recurrent input. And potentially this seems like it could be a more allow more flexible representations where you have some cells that are sharing this predictive state. So for example, the purple cells are hard to see there are predictive of 9. Where the blue cells are saying that the current representation is 8, and this might allow us to have the same cells representing the next predictive state, and therefore sharing between sequence items that are prior to 9. I think it's still possible for this kind of structure to learn many columns by learning similar weights for groups of cells. So it seems like it's still possible to get to that same end state, but in a way that might be more flexible and not force the relearning of predictive state for every input class.
Good exercise, although I would bet very unlikely that's actually what's happening. But it's okay. I'm not saying that's not your exercise. I don't think that's what's going on.
Hey guys.
Yeah.
Will you do me a quick favor and move the mic from behind your laptop into the front?
Yeah.
Thank you.
And then, so kind of taking this one step further, if the goal is to be able to produce these subpopulations of neurons, some of which are representing the input and some of which are representing predictive state, I wanted to try just partitioning the model entirely and forcing these subpopulations to take on these functional roles. And so this is, I'm calling this a flat partition model. So it's flat in that there aren't column level, there aren't shared weights, but we have a subset of neurons that are only taking feed-forward input and a subset that are just forced to take recurrent input. So whereas that could be learned in the flat model, this is enforcing the connectivity to be in this exact fashion. So the red layer there is a flat layer that takes input from the feed-forward, and the blue layer is this hidden recurrent state. They are combined and they produce the inputs to the next recurrent state, whereas the red layer is just taking the next digit. And I've also experimented with a third potential partition that integrates both the feed-forward and the recurrent activations, which is exactly what the cells were doing in the flattened and the kind of traditional RSM model. So this performs the best on the stochastic MNIST benchmark. So on this POGI-9 data set that I was showing earlier, the 8 subsequences, 9 length each, the theoretical accuracy limit is 87.26%. That's the best you can do if you're making the exact right predictions at every time step. And the flat model got to 74% after about 20,000 mini batches, and the flat partition model got to 86% after just 2,000. So it learns extremely quickly, and it gets much closer to the. Sorry? That was the benchmark of the grammar that I showed in the lower left corner of the stochastic MNIST. It's this guy. On the lower left, this is just the grammar that we use to benchmark.
Oh, okay.
So it's the stochastic MNIST benchmark with 9 subsequences.
I did the same guy, no, different guys in the RSM.
Same guy, sorry.
Oh,
Yeah.
okay.
Their lab is
that's
AGI.
proprietary data. Okay.
Yeah.
It's kind of tiny.
Yeah, it's a confusing name. I shouldn't have named it that. But this is the grammar that we agreed to test our models on, so we could
So
compare.
it's the same one used on the paper.
No, it's actually, so the ones used on the paper were fixed sequences, and these are stochastically generated sequences. So they were just putting in 0, 1, 2, 3, 0, 3, 2, 1 over and over again without any uniform random selection. That's a much easier task. So once you add the stochasticity of uniform selection of the next subsequence, it got much, the original model started performing much worse. So that's why I was doing this kind of architecture exploration and all was try to improve that's performance. So that did reasonably well. I was pretty happy with those results, though there is this limitation of the fact that the benchmark we were using was pretty much just second order sequences. There's only a couple of digits that require kind of 3 time steps back in order to predict the next digit. So it might not be quite a difficult enough benchmark. So that's something that we would like to experiment more with. The language modeling is a much more difficult task. So language modeling is typically reported in perplexity.
Actually, even for the stochastic MNIST, I think I should point out we're not actually sending in symbols, we're sending in MNIST images.
Yes.
So in order to actually do this, it essentially has to solve
MNIST, absolutely.
MNIST. So that's something that the traditional temporal memory could not do. And it's actually, it is generalizing from a training set to a test set here. While doing sequences.
So that was an impressive result, even from the first RSM paper.
Yeah.
I think when we added this stochasticity, it became a harder problem because it kind of requires second order sequences at least.
Yeah.
And so this model deals with second order sequences very well.
So if you think about like theoretical typically the best accuracy is on MNIST around 99%.
Mm-hmm.
And for one layer model, it's probably less than that.
Yeah.
If you multiply that by
It's close.
the limit, it's
I think it could probably get to 99% after more training.
Yeah.
And how do you guys do this theoretical?
You look at the sequence and you figure out what's the best thing you could predict at every time step. So it's always impossible to predict the first item in the sequence because you don't know which one you've uniformly chosen. But you can predict, for example, in this case, this particular grammar, you can always predict 2, and you're going to get 3 out of 8 or whatever it is. Yeah, 3 out of 8. The next digit is going to be similarly difficult to predict, and then after that, it becomes deterministic. So you can always get the next items correct. So if you memorize these sequences, so you can.
So Marcus, if you remember, you had made that comment that previously it didn't even have to look at the input; it could just generate the sequence. And we're hoping this is a harder task that doesn't have those kind of trivial answers.
You can't memorize one thing. You now have to memorize multiple things and figure out which one we're in.
Yeah, but it's still only a second order. It's not a super difficult sequence task.
So language modeling is much harder, and in the original RSM paper, they noted that this doesn't get anywhere close to state of the art from things like LSTMs. So language modeling is often reported in perplexity. So lower perplexity is better, where the best possible score is your predicting with 100% confidence the next word in the vocabulary, and you're not predicting anything else. You're predicting everything else at 0, so it's like a point distribution. The percentage there is the next word prediction accuracy, so they got 20.6 in their original paper. The flat partition model gets to 23% and maybe around 150 perplexity after far fewer mini batches. So there's still something interesting and potentially useful happening there, but I have some speculations for what it's doing. So yeah, just as I said, this is sort of disappointing results overall for language modeling. So I think there's either this is a fundamental limitation of this architecture, or there's some things that we're not doing as well as we should be here, and I have some thoughts on that. In general, what the RSM and the RSM related models do on language modeling is they overfit to the training set very quickly. So really regularizing and trying to figure out how to generalize to unseen sequences is the hard part. There's a few things that the RSM authors suggested for doing this. I think there's probably more regularization that we could look at. The concern I have about this partition model is that it's possible for the recurrent layer to be essentially a pass-through for the previous state of feed-forward input, which would allow us to do classification with t-1 and t equals 0. And for the stochastic MNIST task, that's probably good enough because these are just second order sequences. So if you have last digit, current digit, you can do a pretty good job of predicting next digit. If we test with third and fourth order models, I think we'll be able to push it and see how well it does. That's my explanation for why it learns incredibly quickly close to the theoretical limit, is that it's essentially getting direct access. And that would be a problem because it wouldn't be able to generalize very well, because it's not really using the recurrent state of the network as a long-term memory. It's just using it as a pass-through. If that's true, then in language modeling, this becomes essentially a bigram model where we're predicting the next word based on the previous 2 words. And that seems to be, I haven't tested this explicitly, but I think that we get similar perplexity if we just tested a bigram model. So my guess is that there's some adjustments we need to make to force the recurrent input to not just be a pass-through. And there's a couple of ways that I was thinking about doing that.
We tested the LSTM method by page 9 rate work as well. How does it work?
I haven't tested LSTMs on the stochastic MNIST task. I'm sure that it would
It should
solve
work,
them.
yeah.
Very
But we also solved that. So it's really for the language modeling that I think the LSTM shows us what is
so
possible.
you also solved that.
Yeah. The other thing that seems to be happening is we get these repeating predictions. And I think this is common, especially early in training for language models, where you get like, word, the. And so I think that one of the things that might be happening here is that we have this hysteresis of memory. So we're keeping the previous memory state around, and we're doing an exponential decay. And what that means is that the cells that we're predicting the next word are still going to be around at the following time step, and even 2 time steps, 3 time steps into the future. And so what I believe might be happening is that even when there's a correct prediction, those cells that made the correct prediction for the current word are still active. I think we need some way of deactivating those cells so that they don't continue to perform predictions of that same word. They sort of get around this with this inhibition. They prevent the same cells from being active if they were recently active. That seems like kind of a blunt tactic. And I think that we're still going to see a problem of propagating errors through to these previously active predictor cells and kind of reducing their connectivity. Even though they were correct to be active and they helped make the correct prediction, we're going to reduce their connection strength because for 3 or 4 time steps into the future, they're no longer predicting the right word. So this seems like a fundamental problem that I think active dendrites are supposed to help us solve. Because with active dendrites, we can, as soon as a predictive state is confirmed, we can deactivate those cells. That's my understanding of the active dendrite model. And so I think there's an opportunity to add active dendrites to this model as well. I have thought of a couple of ways that we can potentially do that by essentially decoding the actual image that comes in and then subtracting that from the memory state. So essentially saying these cells were successful at predicting this image, so let's remove them entirely. So I think there's a few different ways to do that. So yeah, that's the potential active dendrites. I think stacking and hierarchy are something that the RSM model was designed for. So essentially, if you have a second layer on top of the previous layer, it's doing next memory state prediction of the layer below, whereas the final layer, the layer at the bottom, is doing next image prediction. So this was designed for this kind of hierarchy. And I think that the original authors mentioned that they were finding that higher layers were just learning the exact same sequences. I think that there's ways that we can get around that as well, potentially by modifying the hyperparameters for higher layers, maybe adjusting the decay and inhibition rates to encourage more invariant representations. So I think that this is part of the solution to some of the repetition and other issues that we're having and overfitting, but stacking is not going to be trivial. So there's some work that we'll need to go into that. And then of course, the embeddings that we're using are fully non-semantic. This is a binary embedding. There's no notion of similarity between similar words. And so these models would certainly do much better with a decent embedding. So I think it's worth trying. The reason they didn't use embeddings was because they wanted to see whether or not representations could be learned. But this is if we want to see how this compares to state of the art, we have to use embeddings. Yeah, so I think that's all I had.
I think we can use, so you need sparse distributed representation as input, right? Or is it mono? Or is there
We're generating sparse representations through a sparse masking step, a K-winner step.
so, but,
So you mean like an encoder?
yeah, but.
Yeah.
Okay.
We could look at using a sparse embedding as well. I'm
I
not sure
think
if
that,
it's
Oracle.io.
Oh, they're using
has a
sparse
lot of
embeddings, yeah.
embeddings and sparse distributed.
Yeah, we talked about
Yeah.
potentially switching to
Like,
that. Yeah.
looking at
Yeah. I've tried like Love and WordDev, but I haven't tried any sparse
that.
embeddings.
The way they do it is very similar. I mean,
Mhm.
this is where I saw their promotion video and all that, but it looked very similar for embedding, just generates an STR. So,
Yeah, and they're binary.
yeah, I think so. Yeah.
Okay. Because this model doesn't require binary, but it can use binary, of course.
Isn't the current embedding binary?
The current embedding is
That they were
binary.
Because
using.
it's
Yeah.
a one hot encoded, right?
It's not one hot. It's a strange non-semantic embedding
Okay.
algorithm. Yeah. Yeah. So
I think also you've got a much better feel for the different aspects of all of these partitioning and non-partitioning, and we can also bring it back a little bit closer to the temporal memory model. And active dendrites are a step towards it, but exactly the way that inhibition is happening and the way we're carrying high order state, we're not even sure if this can actually do more than second order.
right, we're not sure.
Yeah,
We're
yeah,
not
so
sure
that's
yet.
something.
Yeah.
Yeah.
And that could just be because of essentially something that we're doing wrong with the way that partitioning is
Yeah.
working or the flat models are working. It's like a local minimum that it's using the feed forward state. I think that if we can get beyond that local minimum by kind of enforcing more recurrent input.
Yes, I think if I had to kind of summarize it in comparison to temporal memory, I think we've gained one thing, which is being able to do the semantic predictions and semantic representations, but we've lost a whole bunch of other things that are in the temporal
Yeah.
memory.
Yeah.
So we need to sort of go
That's a
back.
good summary.
Though notably, the RSM can still learn extremely long sequences, just like HTM can. You can overfit to the training set, get 50% next word prediction accuracy. So that's learned hundreds of thousands of word sequences potentially.
Yeah.
So some things are still there.
Yeah. Cool.
All right,
All right,
That's
thanks.
good, thank you.
Yeah.
Can you show those live?
Yeah, I can.
Also on YouTube now.
Yeah.
I did the slides.
Yeah.
Matt?
Slides are much faster.
Okay, guys, I'm going to cut off the stream now.
Yeah, let me
Thanks.
know when you do.
Thanks for watching, everybody.